We present a computational design pipeline that embeds multiple capacitive touchpoints into any 3D model that has a closed mesh without self-intersection, like these 3D models. The output is a 3D printed object whose touchpoint can all be capacitively sensed with either a single wire or double wire connection. This is possible because our computational pipeline optimizes a phenomena called RC delay. Our computational pipeline workflow starts with the designer generating or using an existing 3D model and then selecting different areas on the model's surface to turn them into touchpoints. After selecting the touchpoints on the 3D model, the second stage of our computational pipeline generates conductive traces that will be routed throughout the model. These conductive traces have two roles. First, they serially connect all touchpoints. Second, the conductive traces are drawn using a serpentine trace pattern which enables them to act as 3D printed resistors. We optimize the resistance for these conductive traces to exploit a phenomena called RC delay. RC delay is the time required to charge a capacitor in a circuit through a particular amount of electrical resistance. Increasing the resistance in a circuit will generally increase the amount of time needed to charge the capacitor, thereby creating a larger RC delay. If each touchpoint in our circuit needs a different amount of time to charge when touched, we can infer what is being touched by measuring the time delay. For example, here is an example RC delay graph for the Stanford Bunny generated from this approach. The distinct RC delay values can signify to a microcontroller which touchpoint is being selected. After optimizing the conductive traces, our pipeline outputs STL files for multi-material printing. We use our computational pipeline to generate several 3D models with embedded capacitive touchpoints. The number of touchpoints in these objects vary as low as 5 and up to 16. We validate the performance of our pipeline by fabricating physical prototypes. Thank you.